Hello, Science Alliance. Hello, IGCSEs. If you're watching live, thank you for the fact that you are letting me teach this at a slightly different time, because I was at a gig in London last night, which is why I'm all wet because I just ran off the train, had a shower, and it's why you can't give me any sympathy for having a sore throat today. It's not because I'm poorly, it's just because I spend the evening going, woo, yeah, woo, like that. Anyway, woo, we're learning about voltage. It's actually lesson 3 of All Ages Electricity. You really don't have to have seen the first 2 lessons. The first lesson was all about static electricity, which is like a totally separate thing. And the last lesson was about current. Let's really quickly recap current, and then I'll do you like a little sheet. So last week we learned about the fact that in metals, this is like a metal wire, there are teeny tiny little particles called electrons that have got a negative charge. And if something's got a negative charge, it means that it pushes away from other things that are negative, and it's attracted towards things that are positive, right? So if you get a wire, and you link it all up together, and then you put something in the wire that has a positive end and a negative end, like a battery. I'm getting worse and not better at drawing battery. There we go. So if you have a look, I said to bring some batteries with you if you had any. If you have a little look on a battery now, you'll see that one end has positive written on it, a little plus symbol, and the other end's got negative written on it. So when you put that in a wire, the electrons are attracted to the positive side and they push away from the negative side, and that's what we call a current. A current is just charged particles that are moving. It's nearly always electrons that are moving. It could be positive particles, but in metals like wires everywhere around your house, it's going to be electrons. So that's what we did last week. This is called a current. It's just charged particles moving is a current. Okay, so that's a circuit because it's wires connected up so that electricity flows, a current flows. You can stick a bulb in there as well. I'm not getting better at drawing bulbs either. Let's put a bulb in here because we'll talk about this later as well. There we go, with a little wire. So I'm just going to give you a little sheet to kind of recap that, to check your understanding, and then we'll move on to voltage. So it's kind of almost better if you weren't here last week, because you can have a guess and really get some brain exercise at these answers. Whereas people who were here last week, I'm looking at you with my teacher face like, come on, can you remember this? So I've got some scenarios here. I just want you to tell me, would these bulbs light up? So situation A is a battery with a wire going from the positive end of the battery through the bulb and then joined up to the negative end of the battery. Then we've got a battery which has got a wire coming from the positive end and back to the positive end with a lamp in the middle. And the same but on the negative side. So would the bulb in B, the positive side, and the bulb in C, the negative side, would they light up or not? Situation D, we've got a battery and then a wire going from the negative end through a bulb and then the wire's joined up to the positive end. Is that going to light up? E, you've got a lamp sort of stuck on the side of a battery, so it's kind of straddling one of the wires from the bulb is on the positive side and one's on the negative side. And F, you've got pretty much the same as the first situation, except there's 2 bulbs in the circuit. So it's battery, wire, and then 2 bulbs, and then more wire joined to the other side of the battery. And if you like, Lara, I know all this already. All right, can you draw them as circuit diagrams? You don't have to. It's a bit of a weird thing to get you to do. Or maybe start with the circuits that you think are the most sensible to draw circuit diagrams of. But yeah, you know. Or if you really want to challenge yourself, you could write down why you've said what answer you've said. So if you're thinking that D does or doesn't light up, can you justify it? Justify your answer. Say why you think that is. Excuse me. I didn't even whoop that hard. I was trying to be careful, but I wanted Corbland to know that I was really enjoying his work. How are you doing? Should we go through it? Let me come up with some ideas. So bulb number 1. Yeah, that would definitely light up. And I've already given you the circuit diagram for that. A battery, wires, bulb attached. So yeah, that's absolutely fine.
electrons in the wire would be attracted to the positive end and repelled by the negative end. So yeah, that's got current flowing through it. These bulbs, no, they would not light up. No. Why? Well, electrons aren't flowing from positive to negative. So this wire, the electrons are just experiencing a positive overall. So it wouldn't make them, they're not flowing, okay? Here's the circuit diagram. I'm really sorry if you drew that. You will hopefully never draw that circuit diagram again. Did you get that? I don't even know what that is. Don't ever do that. Right, would these bulbs light up? This divided people on Facebook the other day. They would not light up. Why not? Well, I mean, I don't know. Maybe the current would flow for like a split second, but not enough to light the bulb up. I've put because it's not a complete circuit. We looked at this last week.
That's what a switch is. A switch is something that breaks the circuit, and if the circuit gets broken, then the current can't flow. It's like we looked at sort of a traffic jam of taxis building up. They've got to be able to flow all the way around. So that's why that one wouldn't work.
Again, apologies if you drew that circuit diagram. Just instantly forget that. That's really weird. Next one. E, would that bulb light up? No, that wouldn't light up. Wires need to go from the positive and negative ends of the terminals, we would say, the terminals of the battery. No, that's not a thing. I don't know what at this point I was just regretting saying you can draw the circuit diagrams if you like, because that's not a circuit diagram. And finally, well, this leads us nicely to our subject, doesn't it, today? I don't know if this battery would light up 2 bulbs, because partly it depends on the voltage of the battery. And this is a good circuit diagram. Well done if you drew that. 1 battery, 2 bulbs, jobs are good. But yeah, we can't say if it's going to light up. We need to talk about what voltage is. What is voltage? There's loads of different ways to describe voltage as a science teacher. Some of them are easy to understand. Some of them are more accurate. Some of them are really not how it works at all, but do make it easier to answer questions, I think. Today we're going to go with the most accurate description that I can think of, and that the Institute of Physics have told me to teach you. Voltage is like a push, okay? Because it exerts a force on the electrons in the circuit. What do I mean by that? I said to bring some magnets if you had some.
I do this all the time on Theatre of Science. I feel like some of you are probably getting really, really annoyed with this by now. Like, Lara, it's just a magnet. We know what magnets are. But if you've got a couple of magnets, hold them near each other and you'll find that one way around they're attracted to each other, they pull towards each other. Turn one the other way around so that they're pushing away from each other. It's so weird. I say this loads, like, how do the magnets know that each other is there? I can really feel a clear force that is not my hands pushing those magnets apart. How do the magnets know that each other is there? They're not touching each other. If someone pushed you like that with air in between, you wouldn't feel the push. It's like the message being carried through the air. What is it? Well, no, it's nothing to do with the air. The answer is magnets have what we call magnetic field lines around them. They've got magnetic fields, so they're sort of detecting each other's magnetic fields. So if that's a magnet, physicists would draw magnetic fields like this around a magnet. These are called magnetic field lines, so you can draw what direction they're going in if you want to, like if you get to GCSE. And what's that? That's not right. And how it works is the closer the magnetic field lines are to each other, the stronger the magnetic field is. So you can see here, like as you would expect, that at the top and the bottom of the magnets, the magnetic field lines are really close together. So that's where the sort of strongest push is felt, right? And as you get further away, you can see the field lines get further apart. So because you know that if you hold the magnets further apart, you don't feel as much of a force because the magnetic field isn't as strong. Well, yeah, magnetism and electricity, they're almost the same thing. So you could call this an electromagnetic field. Charged particles have got an electric field around them as well.
Here we go, there's a little picture. So here's a positive particle and a negative particle, and this is how a physicist would draw the field lines around it. It's an electric field, which is incredibly similar to a magnetic field. So you can see it's stronger, closer to the charges, because these little field lines are closer together. It gets weaker the further away you go. So this is what happens when you put a battery in a circuit, in a wire. Adding more and more batteries makes the electric field stronger, which pushes the electrons more. So in the same way, that I've got to draw this
terrible circuit diagram again now, haven't I? It's not a diagram, it's a picture. But anyway, in the same way that if you had loads of teeny tiny little bits of iron, say, on the table, and you put a magnet on the table, all the little bits of iron would experience like a push or a pull, wouldn't they? They'd move around. When you put a battery, another terrible picture coming up, folks. Wow, wow. When you put a battery in a circuit, you've got an electric field. It sort of generates this electric field, which the electrons feel, yeah? So like tiny little bits of metal, say, sprinkled on a table with a magnet. These electrons feel a pull and a push from the magnet. They experience from the battery. They experience a force, and that's what makes them flow around. It's not actually just the battery that creates this electric field, but it's all we're going to talk about today. And what happens, I've written here, what happens when you push something? Look, I actually wrote it down. What happens when you push something? You know, just do it. Say maybe you've got a battery, because I said to bring some batteries with you. Just give it a push. What are you doing? What happens? What a silly teacher question. Loads of things happen. What is the right answer, Lara? Just tell us. What happens when you push something? Well, hello. It's not. What has happened is I have eaten some food. My body has stored the energy of that food, if you like. And when I push the battery, it's not very good exercise, is it? But technically, I am using up some energy, and I'm shifting the energy, we would say, to the battery. So I have energy stored in my body. I push this battery. I lose some of that energy. I'm going to have to eat more food after all this pushing. But the battery has some energy now, right? Because it's moving. So it's the same with the electrons. The battery, we would say, like shifts its energy to the electrons. And then, of course, you have a bulb in the circuit. I'm going to stop talking in a minute and give you something to do. You've got a bulb in a circuit, and these electrons shift their energy to the bulb. So, just for the sake of completion, because I have colours, yeah, the bulb lights up. Right. I was going to give you a sheet. I have to tell you something else. So if you have a battery with you, have a little look on it. Hopefully you'll see a number and a capital V. Just show you mine in case you haven't got one. There you go. So this is a 9V battery. What that means is the V stands for volt. So you measure like distance in meters. You can measure time in seconds. You measure, well, you measure voltage in volts. But what a volt actually means, this is where I take you to the sentences so that I don't just blah, blah, blah and make you all confused. A volt actually means energy per charge. So energy is measured in joules, right? So like a 3-volt battery means each charge in the circuit is getting 3 joules of energy. Is that okay? Like a 5-volt battery would mean 5 joules of energy per charge. So voltage is telling you how much energy per charge. Yeah, is that right? So for energy cannot be created or destroyed, right? You can't just make energy or get rid of energy. So if you have this circuit, a battery with wires connected to a bulb, a 3-volt bulb is designed to work with 3 joules of energy per charge. So if you added a 1-volt battery to the circuit and this was a 3-volt bulb, the bulb wouldn't get enough energy, right? Because it's only getting 1 joule of energy per charge and it really wants 3 to light up properly. So the bulb might be quite dim. And if you added like a 12-volt battery, that bulb would be getting 12 volts per charge, which is too much. You get too much energy and it might melt. Not like that, it's just a good effect, isn't it? Shall we look at that with the circuit diagram, and then I will give you hopefully what is quite a simple sheet. So I've got my little snappy circuits here that I got from a charity shop. I've got a bulb here which is 2.5 volts, okay? And I've got two, we talked about last week, these aren't, one of these things is actually called a cell, and more than one is a battery, but I'm just going to say batteries to mean 1 or 2 or 3 or whatever. But anyway, if you look at these batteries that I've put in here, can you see that they are 1.2 volts? So I've got 1.2 volt and a 1.2 volt, which altogether makes 2.4 volts. It's pretty close, isn't it? I mean, they're probably not fully charged, so it's probably not actually giving 2.4 volts. But hopefully, if I connect them to this 2.5 bulb, we will see. Yay! That seems to be... Oh, that was weird, wasn't it? It did a really bright flash and then it... Okay, let's
Let's see if these batteries are a little bit more charged up. Oh, that's better. Yeah, look. So that's obviously these have got more energy per charge. They're more charged up. That's great, isn't it? And then if I plug in my bulb here, that's a 6-volt bulb, what are we going to see? So this bulb really wants 6 joules of energy per charge. And here we've got about 3, maybe like 2.5 volts. There you go. That's what we were expecting to happen, isn't it? It's dim. It's not getting enough energy to work properly. Okay. Have a look at this sheet then. Fill in the gaps, please, to make these circuits work properly. First one done for you. I've been too kind to you here, really, but do these. So question 1, you've got a 3-volt bulb, and what battery would that have to be to get the bulb to work properly? It would also have to be 3 volts, yeah? 3 joules of energy per charge for that bulb. Lovely stuff. Question 2, you've got a 4-volt bulb, and you've got 2 batteries here. One's 2 volts. What does the other one need to be to make the 4-volt bulb work properly? Question number 3, you've got 2 3-volt batteries in this circuit. So what bulb would you plug in to make that circuit work properly? Question 4, you've got 2 1.5-volt batteries, sorry. You've got a 2-volt bulb. So what's the voltage of that other bulb if that circuit's going to work properly? Question 5, 2 1.5-volt batteries connected to a bulb of mystery voltage. What is that? And actually that circuit's still not working. Why not? That rustling in the background is me attempting to really quietly blow my nose. How are you getting on? Should we go through it? Oh, ow. Oh, such a sore Okay, let's do this. So number 2, that's going to be a 2-volt battery, yeah? 2-volt batteries connected together makes 4 volts, gives 4 joules of energy per charge, so that 4-volt bulb would work properly. Number 3, you've got 2 3-volt batteries next to each other, so that's going to be a 6-volt bulb, hopefully. Number 4, you've got a 3-volt battery altogether, 2.5 and another 2.5, but one of the bulbs is using 2 joules of energy per charge, so hopefully that would be a 1-volt bulb to get that working properly. And question 5, that's going to be a 3-volt bulb, because that's how much the voltage of the battery is altogether. And well done if you spotted that circuit is still not working properly, because we talked about this last week. This person's connected their batteries incorrectly, so the negative side and the negative side are both facing outwards, so that is not going to generate this electric field which is going to apply a force to the electrons to let them shift energy to the bulb. Right. So I said to bring some batteries with you if you had some. An assortment of batteries. We need to think, does the size of the battery affect its voltage? Have a look if you've got some. Maybe I should have said, how does the size of the battery affect its voltage? That would have been a better question. So have a look at yours if you've got any with you. If you haven't got any with you, you can look at mine. How does the size of the battery affect its voltage, do you think? So I've already showed you that this big one, the supercell, is 9 volts, and this kind of medium-sized one is 1.2 volts. There we go. So I've got a little button battery here, and then I've got it's like a normal cylinder battery shape, but it's very small. Which one do you reckon has the smallest voltage of those 4, and which one do you think has the biggest? It's probably just guessing, so I'll give you like 5 seconds, I don't know, to just guess. Which one of those batteries do you think has the highest voltage and which one has the lowest? Have you made a decision? Okay, so the big supercell, that's 9 volts. The medium-sized one is 1.2 volts. This button battery here is 3 volts. You see that? 3 volts. And this teeny tiny little one is 12 volts. What? Gasp! Have we all learned something here? Size doesn't make a difference at all to what the voltage of a battery is. There you go. That was interesting, wasn't it? Moving on. The voltage of the electricity in your house is probably, well, if you're in the UK like me, it's about 230 volts. That's a lot of energy. I said if you have like a laptop charger or a mobile phone charger that you're allowed to look at to bring it with you. So the electricity coming into your home is about 230 joules of energy per charge. That is a lot. Yeah, don't mess around with electricity in the house. But most laptops operate with about 19 volts. So my question to you is, your puzzle for this bit is, why doesn't your laptop melt whenever you plug it in? Or maybe not yours, but if laptops want 9 joules of energy per charge, 9 volts going through them, and the electricity coming out of your plug is 230 volts, why doesn't your laptop or a mobile phone just burst into flames as soon as you start charging it? People were giving me some brilliant answers on Facebook. I mean, some people just knew, but it's really interesting if people don't know, like where their thinking goes. Someone will say, no, there must be something in the plug that like somehow blocks it. Oh, that was a great answer. Yeah, if you have a look at, well, I've got my laptop charger here. If I unplug this bit and we look on the bottom, you will see that it says output. What can I point with? I'll point with this tiny little battery. Oh, yeah, input is 100 to 240 volts. You see there? Input 100 to 240 volts. So I'm going to make you feel travel sick. So that's the voltage that's going in, like from your electric circuit, and the output is only 14.5 volts. So the reason that you've got this big sort of brick-like thing on the end of the charger, why you don't just plug that into the computer and then plug the other end in, is because there's something called a transformer in there, not, sadly, a robot in disguise, a different kind of transformer, just a load of wires kind of coiled up. But yeah, it converts the voltage from a very high voltage to a lower voltage, and they can go the other way as well. That's good enough. It's clever. Okay, you lot. Right. I have to tell you, I have to break something to you, which is going to be really annoying, and then we'll do one last set of hopefully fairly simple questions. Well, I don't know actually, and then we'll do a little quiz at the end to check your understanding. So the thing that I told them on Facebook that I have to tell you, which has annoyed like every physics student since we started learning physics, is I keep saying that the electrons in the wire are attracted to the positive end of the battery and repelled by the negative end. That is true. That is what's happening. That is how the electrons are flowing, because negative things push away from negative things. But when they first discovered electricity and started using wires and things to let current flow through them, they didn't know that electrons existed. They didn't know what was happening. And the convention became to say that electricity flows from positive to negative. Not actually what is usually happening, but any kind of circuit that any kind of like question about circuits that you answer, or if you've got an electronics kit, how you have to put that together is you have to imagine that electricity flows, current flows from, so right, that's the negative end of the battery, that's the positive end of the battery, so current. The convention is you imagine when you're working with electricity that it flows from positive to negative. And this is when every physics student starts going, why don't you just change it? Like, no, we can't. Sorry. Also, like, don't forget, current isn't always electrons. It could be positively charged particles. So sometimes it might flow from positive to negative. It never will if it's a metal.
and you're dealing with it. But, you know, I'm sorry, okay? It's not my fault. But yeah, if you're using the electronics kit, I keep saying the thing that is true, and you need to know the convention, which is the other way around. Anyway, I'm not going to test you on that. It's just something that if there's physics teachers watching, they'll be tutting at me that I haven't told you that. Okay. Whew. Have a go at this question for me then, and then we'll crack on with the end of the lesson. The bulb in this circuit, got a simple little circuit here, one battery, one cell, and some wires connected to a bulb. So the bulb in this circuit is shining normally. Can you say, looking at these other circuits, how bright the other bulbs are? Would they be bright, or normal, or dim, or would they be out? Hold the phone, Lara! What information do you need that I have not given to you? You can't just press on and answer this question. I've missed out some crucial information. What have I missed out? Well, on Facebook, a lot of them were saying you've missed out the voltage. That's true. I could tell you what all the different voltages were, but instead I'll just say all the bulbs and batteries are the same. So we'll say that all the bulbs like A, B, C, D, they're all exactly the same as this bulb, and all the batteries that you see are exactly the same as that battery. They're all fully charged and stuff. So if a battery connected to one bulb by sort of average length wires is shining normally, how are these ones shining? So you've got one battery connected to two bulbs. How would they be shining? You've got a battery connected to a bulb, but the battery is now flipped around, so positive and negative are the other way around. You've got two batteries connected to two bulbs, just with wires going around in a circle. You've got the same one as the first one that's shining normally, except the wires are shorter now. And you've got G, finally, the bulb and the battery are the same as the first one, but now the battery's on its side. How are those bulbs shining? Should we go through it? So A and B, the bulbs in this circuit that are sharing the energy from one battery, they are going to be dimmer. Or well done if you said out. I think dim or out would be a really good answer to that question, because we don't really know. But yeah, they would be dim, or you could have said out, or both. C, there were a surprising amount of people on Facebook telling me the other day that if you flip the battery around, that bulb would go out. No, it definitely wouldn't, right? That is just a completely... I think people were getting confused and thinking what I'd said the other day, like, you know, if you actually turn one of the batteries in a pack round or something so that the two negatives are on the outside or the two positives or whatever, that would make a difference. But I didn't do this last week, but it's quite a good demonstration, I suppose. It would be like the difference between doing that. Oh, I've used the 6-volt bulb. I'm panicking because I want to get to the answers. Wasn't going to do this. It would be the difference between doing that and then just like turning the bulb around. Doesn't make any difference, right? It would be the current flowing in the opposite direction. Oh, no, it wouldn't even be in the current flowing in the opposite direction in that case. There are circuits where the direction does make a difference to whether things work or not, and we will talk about them a little bit later on. But yeah, if you turn the battery around, the current here and here are flowing in opposite directions, but the bulb is still lighting up, it's still getting the energy that it needs. D and E, they would be normal, because now you've got two bulbs in the circuit, but you've also got two batteries, so they're still getting the same share of energy. F, I thought this might catch you out because we've been talking about like how far the electric field would work. F and G are actually both normal. I was thinking like if you've got an electronics kit, you might be thinking that if you use this tiny little wire or this really long wire that the electric field from the battery might kind of not stretch as far and make a difference, but that's not going to make a difference. If it was like miles and miles and miles long, then it would, but that doesn't make a difference. Okay. I hope you enjoyed that. Now we have the fun quiz. It's actually just like 4 more questions, but it's a quiz because it's at the end, right? So here we go. And it's multiple choice. So if it's multiple choice, it's a quiz. Let's see how much you understood of this lesson. Here we go. These batteries are fully charged. So you've got 2 batteries here. Well, yeah, 2 batteries, let's say, in a circuit connected to 2 bulbs. They are fully charged. Would the bulbs light up normally? Is the answer A,
yes, B, no, or C, need more information. 2 batteries, fully charged, connected up to 2 bulbs. Would the bulbs be shining normally? A, yes, B, no, C, need more information. The answer is, well, if you said A, then well done, because you're thinking about the fact that it's each battery could support each bulb. But the answer really is need more information, isn't it? Yes, because if these are both 6-volt bulbs and these are both 1-volt batteries, then they wouldn't have enough energy to operate. So well done if you said needs more information. This 4-volt bulb is lit up normally. What is the voltage of one of the batteries? So we've got 2 batteries here, 1 bulb. The bulb is 4 volts. What is the voltage of one of the batteries? And be a little bit careful here. I kind of made a mistake here, and then I kept it in because I thought it was quite an interesting mistake. So what I was thinking was, 2 volts, because 2 volts and 2 volts will support a 4-volt battery. But I didn't actually tell you the batteries were the same, were they? So I've made a mistake there, like that. It could be a 1-volt battery, and then the other battery could be 3 volts, and then you would add those together, and that bulb would still be getting 4 volts. So yeah, interesting. It just shows that GCSE questions are hard to write. You've got to think about things. What is another way of saying volt? Is it A, volts per charge, B, charges per joule, or C, joules per charge? What is another way of saying volt? The answer is joules per charge. Joules is how you measure energy, so it's like the amount of energy per charge. Oh, that's the other thing that I wanted to tell you. Again, these little things that I wouldn't bother to say in the classroom because I'm worried that they might confuse you. But if you're home educating, you've sort of got time to process it more. When I say charge, 1 electron is not 1 charge. So we're not talking about how many joules of energy each electron has. 1 unit of charge is actually quite a lot of charge. You need to kind of add up lots of electrons to make 1 unit of charge. I'm never going to test you about that. I just didn't want you to go it because you'll obviously be imagining like the amount of energy per electron, which is, so 1 volt is 1 joule of energy per charge. It's not 1 joule of energy per electron. Lots of electrons make 1 unit of charge. It doesn't matter. It's just so you know, okay? Right. Finally, I think this is the last question. Batteries make the electric fields around circuits stronger. Which of these could affect how strong the field is? So it might be 1 of these, it might be 2 of these, it might be all 3 of them. What affects how strong the electric field in a battery is? Is it in a circuit is? Is it A, how many batteries are in the circuit? B, the voltage of the batteries? Or C, the size of the batteries? Which of those could affect the strength of the electric field? Like how much force the electrons experience? The answer is... You got something? It could be how many batteries are in the circuit, or it could be the voltage of the batteries. So size of the batteries doesn't make any difference at all. That doesn't tell you what the voltage is. But yeah, like if you add more batteries to the circuit, even if they're tiny, puny little batteries, adding more, as long as they're fully charged, would still increase the strength of the circuit. But you could take 1 2-volt battery away and add a 12-volt battery instead, and that would increase the strength as well. So the voltage of the batteries also makes a difference. Right, well done you lot. That is finally the end of the lesson. This is where I have to do my little ad, because some of you might be new and might not know how I do these lessons for free. It's such a cool business model. I just like accidentally fell into it, or you kind of like told me what to do. So I stream all of my lessons for free like this. I stream them on Facebook, I stream them on YouTube. I do an IGCSE physics lesson. I do a Lego story show, which is coming up quite soon after this one. I do these all ages lessons. The lessons, not the Lego show, but the lessons have free printouts as well. It's all on my website if you're watching on Catch Up. And I just say to people, if you want to support me, you can. So you don't,
you don't really get anything extra for supporting me. I just want it to all to be available to everybody. But if you go to my About section on YouTube, or you go to my Facebook page, you'll see this link to this website called Ko-fi, which is where you can sign up to send me £5 a month. And yeah, it's just working really well. Enough people have sent me £5 a month that it could be my job. And yet, hopefully £5 a month from you isn't that much for, like, you know, what you're getting in terms of lessons and stuff. Just going over to my Facebook page, because there are no comments on YouTube, but you can put comments on Facebook posts. So when I'm live on YouTube, I put a little note up on Facebook saying, you can comment here if you want to. Hey, I've got comments. Oh, that's nice. Let's have a look at these comments. So yeah, there's only the only thing that people who support me with £5 a month get, that people who don't support me don't get, is Theatre of Science magazine. I write a Theatre of Science magazine to just kind of gently encourage you to sign up, and also to say a massive thank you for signing up. So obviously I can't send you this for free because it costs me money to make it, and it costs me increasingly amounts of money to post it. But yeah, I write it. Graphic designer husband graphically designs it. I'm so proud of it. It's very unreliable. My supporters are just lovely, patient people. They just know that I write it, and then when I'm happy with it, I get it printed and I send it out. And sometimes it takes me ages. This one took ages, so it's actually kind of super special. So you're lucky if you get this one. It's got a choose your own adventure. It's all about acids. So it's got a choose your own adventure about you go back in time, and your knowledge of acids decides whether you get like trapped in time or whether you get to come back again. It's got a comic that I wrote. It's a true story about acid rain and what happened there. It's got a which acidic object to you quiz. It's got loads of good activities in it. It's quite a few of which I didn't know about until I started researching this magazine. You can do some turmeric art, as long as you're not allergic to it. You can do some etching. Yeah, I'll send you some sweets, which I don't think have anything in it that any of you are allergic to, because there's an article about why acids taste acidic. Don't just taste random acids, but these sweets have got 3 different types of acid on them, and you can taste them and then learn about why acidic things taste sour. And I'll send you some little litmus papers that you can use to test the acids around your home. And if you're signing up for the first time, I will send you some rainbow glasses. They make you see rainbows. They're amazing. So you could sign up for £5, get all that stuff, and then not support me anymore. That doesn't often happen. I think it's because I don't advertise. So the only people who find out about it are the people who are sort of enjoying the lessons. So like want to support the lessons, which is lovely. So I feel like I can, so that's kind of why the business model works actually. I think if I advertised, I'd just end up sending off loads of packages that are worth £5, and then people will cancel. But yeah, it's fine. It's working. Oh, Lana's here. And Finley. Hello. Oh, nice to see you. Oh, we will see you at Lego Story Show later. Wait, so you're not here? I don't know. Anyway, hello you lot. I'll see you soon as well, if not just. Hello, Magnus. Hope you enjoyed your train ride. I did. Actually, I really loved my train ride. There were so many good clouds. Oh, hello, Bob and Amanda. Hello. What? Bob and Amanda are here. We finally managed to get to a live lesson. Yes. Hello. Nice to see you. Not see you. That's creepy, but you know what I mean. Nice to know. Nice to experience you in real time. Hello from Arthur and Abba. Gone watching with Grandma Ra as Mummy and Daddy have gone to see the Foo Fighters. Oh, Grandma Ra stepping up. Nice work. That is very cool. Gone to see the Foo. Oh, Edmund's watching live. Yes, and someone's replied to Edmund. Hello. He thought that the bigger the battery, the bigger the voltage would be. Hooray! Taught Edmund something. Doesn't always happen. Edmund knows a lot of stuff. Edmund, I'm so glad that I managed to teach you something today. He reckons that electricity flowing from positive to negative could only ever happen if the circuit was made of antimatter. Ooh, yeah, nice. Yeah. Like positrons. It wouldn't work, would it? Because they'd just instantly like connect to an atom and kind of disappear. But yeah. Edmund thought the mistake you made in the question was that you asked about the voltage of one of the batteries instead of asking the voltage of one of the cells, as both cells together make a battery. He remembered last week's lesson. It's just music too, my teacher is. Hello, Lewis. Sneaking in at the end there. Hello. Good to see you. Again, not see you, but you know what I mean. Right, I better go because it's actually, blimey, I didn't plan this very well. It's nearly Lego Story Show. It's Lego Story Show in what is that? 18 minutes time. And there's just bits of circuit all over my desk. I need to rearrange my Lego, so I better go. Oh, good, you are here. Lana and Finley are here. They're just also going to be here next. Brilliant. All right, well, I'd better go for Lana and Finley's sake so that Lego Story Show isn't a total disaster. So I will do that. Thank you for coming. I will see you all. I'll see some of you in 18 minutes for the Lego Story Show about the difference between a swallow and a swift and a house martin. I'll see some of you next week for a lesson on, I think we'll do resistance next, and then you've got all the things you need to know about circuits for us to do really cool questions. Right, I'll see you later. Bye.